it seems that the webinar just started. So hello everyone, this is Luboš Pirkl from CFD Support, and I would like to welcome you to a webinar where we would like to show you a project which is about the simulation-driven optimization. The object is Axial Fun. So we created a quite comprehensive Axial Fun simulation-driven optimization study. And in today's webinar, we would like to show you what we have found and how easy it is to create such a complex workflow in our simulation environment called TCAE. So I hope all the techniques work well. So if not, let me know. And I think we can start. So the webinar is being recorded. So the recording will be later made publicly available on our YouTube channel. So feel free to find it there. So there will be a recording. You can ask questions in the latest part of the webinar. There will be a Q&A session where we will answer all your questions. So there's a special window where you can ask your questions. The good news is that we will answer all your questions. We will pick the most representative questions in the webinar, and all the other questions will be answered later via email. You can be sure that all the questions will be answered. And I hope we can start. So I am here today with my colleague, as usual, with Radek. Radek is our head engineer and also great engineer and developer. So let's check the connection works. Hello, Radek, can you hear me?
Yeah, hello, Luboš, and hello to the audience. I can hear you, I can see you. So everything seems to be almost perfect.
Great, that's perfect. Okay, so I think it seems that we are ready to start. So
definitely.
Okay, yeah. So let's do that. So Radek, I think we can switch the camera off, and then let's continue without them. Maybe we can get back later. So okay, it seems we've switched the camera off, and yeah. So I'll start. So I'll start with a general introduction and about the project and about also our company, and later I will hand over the presentation to Radek, and he will continue with a little bit more with details, and then we will get back together, answer your questions, discuss a little bit what we have found, and then we will conclude and close the webinar. All these sound like a plan, so let's start. So as you know, our company is called CFD Support, and it's located in Prague, Czech Republic. We are doing well, and we are dealing with engineering simulations. I think this is pretty known. Our flagship product is a comprehensive simulation environment called TCAE. It's simulation software where the engineers can simulate especially CFD simulations and also FEA and acoustics and optimization. And it's based on open source. It consists of like individual software modules. They're like standalone tools. The users can decide how to use them, if use them at all. There are a couple of principles we follow with TCAE. That's very important to us to follow these principles to that. So TCAE is flexible, so the users can play a puzzle, so they can use the individual modules, connect them to other existing solutions like in-house codes, commercial codes, other open source codes. They can script it, they can use it in really multiple ways. So it's extremely flexible. It's unlimited, so the business strategy is to provide no limitations at all, I would say. So there are no limitations on number of users, cores, sessions, jobs, hardware installations. So you can be sure that the users can use their resources to the fullest. It's definitely focused. It's not a general purpose software. It's automated, accurate, focused software. The main focus is turbomachinery applications and external aerodynamics. So these two applications are like golden eggs. We really have simulated a lot of them in the past, and we are ready to prove it. I think I can continue that there are a lot of benchmarks that are available. So over the years, we made dozens of benchmarks and compared the accuracy of TCAE with measurements and other simulation codes. That's important. Another important principle is that TCAE can be run from anywhere and be run anywhere. You can run it on laptop, you can run it on desktop, PC, cluster, cloud, you can work from home, you can run it in your office, you can run it on Windows machines, you can run it on Linux machines. The same workflow is consistent from everywhere. That's important for us. And another important principle is TCAE is based on open source. So in the lowest level of TCAE, there are a lot of open source pieces. There are more than 60 open source projects. TCAE, for this reason, TCAE is also partly open source, and on the top level there is graphical interface which is set in ParaView. So it's really a big thing because there are a lot of users of these open sources everywhere around the world who contribute to these open sources, and we have this privilege to integrate these processes and this software into this solution. And on top of this open source work that has been done already globally, here at CFD Support we have spent more than many years of team development of these tools to test them, to implement them in a smooth automated workflow, and TCAE is a result of that. So it's the point is a lot of work has been done, an enormous amount of time has been spent to deliver this, and the value, we believe that the value is huge. In the next TCAE version, we believe it will be ready in September, October later this year. The work name is TCAE 23.10. There will be hopefully a new simulation module which will be called T-Base, and this will be a really big thing. In our opinion, it's tremendous shift to something what has not been here before. So far, we have been doing things that were available in a way from other, let's say, from other companies in the market, but this is something totally new. We will allow our users to store all the results that has been ever simulated in special databases and keep the most important parts and essences of simulations, and later it will be possible to use data mining and of course machine learning and artificial intelligence to get the results out of it, very accurate results out of it in seconds, not in days, weeks, or hours. So it will be a tremendous shift, and this is something really big, and we are excited about it already because we have the first implementation. We did it already, and it's very promising for the future. So the new module will be released later this year. Today's webinar is about optimization. We believe that the optimization is part of this, of all of these, and it's a big thing because as you know, in the past, engineers were simulating like individual points over the time and get some lessons and ran simulations one by one. Optimization is big thing for us. We believe it's a large shift from the trial and error method to the conceptual search for the best possible. We are engineers, and we believe that the world consists of parameters. And if you know the key, if you play with the parameters, then you can move systematically forward. As you know, any simulation has a lot of parameters. Any industrial product has another lot of parameters. So we are talking about huge, infinitely huge parametric spaces, which are definitely absolutely impossible to get by a human mind, because human mind can imagine like 2 or 3 dimensions, right? But we are talking here about the parametric spaces that have hundreds of dimensions. It's absolutely impossible to take it, get it, to imagine it with a human mind. So we are talking about infinitely complex parametric spaces that need to be solved, and the point is it has to be a machine. It has to be an algorithm that solves this, because human mind is absolutely incapable of that. So we believe that the optimization is a tool for consistent looking into these parametric spaces, and they have to be automated, and automation and optimization avoid human error and the human limits. So we are sure of this. This already happened, and it happens everywhere, and that's the current reality. In today's webinar, we would like to show you an optimization workflow. It's simulation-driven optimization workflow on Axial Fan example. So it's a relatively complex workflow where all the steps are done in TCAE. It's connected to a special geometry builder called OpenVSP. So Radek will talk about it a little bit more in detail. But it's a simulation loop, in fact, that a lot of simulations, or any number, users defined number of simulation, is done in a loop. And based on the previous results, the optimization algorithm decides the new set of parameters, creates a new candidate, simulates the new geometry, and again, based on the results and based on all the previous results, it suggests a new set of parameters, and again it creates such a loop. And hopefully, and yes, it happens, the simulation loop converges to the best possible set of parameters, which is the winner, or definitely a candidate for production, because it has best the goal function and the optimization function. Sometimes it's called objective function. So yeah, we created such a workflow, which is by the way public, so anyone can download it and try it himself. So it's this TCAE workflow where the module TOpt, when it's enabled, it let's say run a couple of DOE, design of experiment points. Everything is user defined, by the way. So the user says what's gonna happen. So in this particular case, we have prepared such workflow where the geometry is simulated, and based on the results, the new set of parameters is suggested. This OpenVSP, which is great open source originally created for airplanes, but it can be used also for many other applications. It creates a new geometry based on parameters, and this new geometry goes to the meshing process, goes to the simulation CFD process, and then it goes to the back to the decision whether the optimization process is converged. If not, again the new parameters are suggested, new geometry is created, and again this loop is running as long as some convergence criteria is met, and then the simulation is stopped. So it's a relatively complex workflow, but it's nothing that difficult. It's it's relatively straightforward, and it's definitely with our help and with our technical support, everyone can run it successfully. So it's this, and maybe it's time to ask Radek to give his opinion about it and show us a couple of details.
Okay, thank you, Lubos. So I will directly dig in, right?
Yes, we can see your screen, so the stage is yours.
Great, thank you. So let me first introduce the today's, let's say the today's example or the study. So you will find it on our web page. You can find it in the case studies, in the Axial Fun optimization section, and here you can read and find all the information about this case. So you can find all the reports, simulation reports, the PDF report about the study, and all the important information. So I will more concern, or I will more focus on the principles rather than to how to say dig deeper into the specific setting of each parameter. So this webinar will be more about the workflow and about the results, processing and reading and all the outputs. So it will be more general than more focused on very particular setting of each parameter during the workflow. So about the Axial Fun optimization. So first of all, when we are starting any project, what we need is the input data. So for this case, usually the input data are the geometry, are the set of parameters for the like flow parameters and simulation conditions. For the TOPT, we need to have a parametric model, which is usually a bottleneck for these kind of geometry optimization applications. And yeah, this everything must be concerned, and everything should be prepared to prepare a nice workflow and nice study with great results at the end. So in this case, what we would need is the input geometry and the parameterized part of the model, which in this case are the blades. So we will be parameterize just the blades, the shape of the blades, and we will be optimizing it to achieve the best efficiency performance of this Axial Fun. So what we would need at the beginning, let me just open this case just to follow up the input geometry, which is pretty simple and straightforward. The most complex thing is the parametric model of the blades. So for the input, so the first part when we would like to simulate something is the geometry. So in the T-Mesh module, as an input, we would need STLs in this case. Let me visualize the geometry. Yes, perfect. Okay, let me just look what is inside. So I will just set the opacity. Okay, this would be fine. And we have 3 components. So basically, I think this case was taken from some experiments for the acoustics which we have made, and then we decided it's very nice case to be used for the optimization of the Axial Fun itself with respect to the efficiency. So the domain is split into 3 domains: the inlet part, which consists of the general inlet, then the wall, the casing of the inlet chamber, we can call it, interface to the rotor, and some shroud part of the rotor. Then we have the rotor itself. So here we have the blades. So this STL will be updated after each optimization run using that open VSP program. So I will show you later. And all the rest, all the STLs, all the other STLs are keep constant because we don't want to optimize them. So we will just optimize the blades. So only the blades will be changing for each optimization run. And the third component is just the outlet chamber, again with all the boundaries and the outlets. So this is pretty simple model which you create in any CAD format. It's pretty simple shapes. You export it just once, and only the blades will be parameterized and will be connected to the T-mesh and to the whole loop every iteration of the optimization. All right, so for this for the parametric model, we have chosen this OpenVSP program. You can access it very easily. Just type OpenVSP. You can click here to get started. You can download it, install it, and use it by your own. There are nice tutorials, or they call it OpenVSP Ground School, and you will find all the basic manipulation, geometry parameterization. For example, here for the propellers, there is a section which learns you how to design the blades for example propellers in general, but it can be applied to the axial fans as well. So this is it. So now let me just show you how the parametric model looks like as an example. So it includes the graphical user interface where I will open our geometry. So I have it on the D drive. I have here directory webinars. It was too much. Here's just a single click, not the double click. Axial fan optimization, and here in the geometry builder, we have this project from OpenVSP, which our colleague Thomas has developed and created. So basically what we have here is the model of the axial fan blades. So in this case, we have just the blades. And for example, just to see the whole geometry, we can import the STLs just to see how it looks together with, for example, hub. Okay, all right. Here we have hub. And for example, we can also, if you want, we can also include the shroud just to see the full model here. But the shroud and hub will remain the same. Yeah, so there was not necessary to model it here. Right. Okay, so this is our case, basically our geometry. And now you can decide what you would like to parameterize. You can change the thickness or the chord length or whatever with respect to the radial direction or whatever. And here we have chosen 4 parameters, which we understand as the most influenced, which will mostly influence the efficiency, but in general it depends on the goals, on the user's experience, on the experts who's developing Axial fan for years, so they have some internal know-how what is the best to adjust to achieve better performance. But let's say we just for this action, for this for this study, we chosen 4 parameters. So first one is this beta 3/4, which is basically the twist, standard twist of the blades. Maybe I can also show the blades in this manner, right? And here's the beta. So I think we have chosen something, the limits about 22 degrees. So if you can see immediately, I change this parameter. The geometry is adjusted accordingly. And for example, the maximum number will be 36. Yeah, so this will be our optimization range for this parameter. Then, of course, there is number of blades. Yeah, so you can add blades to the design. All right, so this is the second parameter. And then the third parameter is the chord length. So we decided to change this parameter. So not the profile itself, but the overall chord length of the each section of the blade. So this is the length, chord length, or chord parameter with respect to the radial position, relative radial position. Yeah, so this is the hub side, and this is the shroud side at a given radius. So as an example, so this is, for example, yeah, the short version of the chord, and I think the maximum we have 0.56 number. So you can see that it's longer. And the last one, if I remember correctly, then we can just check in the TOP setup what was the thickness. So the thickness, the minimum thickness was 0.12. Okay, it was not so visible. So if I make it more thick, 22, then you can see, yeah, that the blades are much more thick. Maybe it's too much. I think the limit was just 21, sorry, or 20 maybe. All right, so you can play with this, and of course you can add more parameters and play with the geometry. All right, then you just save the script. And what we have there, if I go again to the disk in the geometry builder, so you will save just the VSP project, and then you can export the script. It's called VSP script, which gives you the commands or functions which adjust these chosen parameters via this script file. So then you can just call the VSP in console, give them the project file and the script, and based on this script, these parameters are adjusted. And basically this, and this is then connected to this file, templated file. So with which, using the initialization script, maybe I will show you later, is connected to the TCAE and to the TOPT, and TOPT adjusts these parameters accordingly to each optimization loop. And then before the tmesh is run, new geometry is created, exported as STL, and then used for the meshing. Fine, so we can close this, and then whenever you will have it, so basically we have all the set of STLs, and this blades STL is exported every optimization loop and is adjusted from the STL, and in the tmesh module we simply say, okay, the STLs will be read from this particular directory, and then the workflow is the same like you do an usual setup of the meshing for the given geometry. Yeah, so we have three components. Each component has some basic mesh refinement, then the local refinement on the blades are set, and many other parameters like refinement region can be set to have more refined mesh near the inlet on the suction side or on the outlet side. So the standard meshing is done. What you need to keep in mind that if the geometry variation is, let's say, much wilder, so you need to, for example, export in advance two extremes, two extrema, for example, for the parameters. Try to mesh them if both variation are meshed correctly, and then we are satisfied with the mesh, which needs to be really carefully done, because then if something is wrong with the mesh and you run it the optimization on the bad mesh, then you get, of course, wrong results, and days of simulation will be gone. So just keep in mind that your mesh must be really nice, or what you would expect for the optimization. Of course, if you optimize something, you don't want to have dozens of millions of cells if it's not really required, because for nice optimization you need hundreds, maybe thousands if you have a lot of parameters, optimization parameters or design parameters. So you need to keep in mind that what you can afford, basically, what is your performance of your cluster, how many loops or iteration you can run, somehow make some yeah, make some balance between the accuracy and the time complexness or time consuming of the simulations. So this is the T-mesh. When you are satisfied with the mesh, you can go for the TCFD, so to set up the CFD simulation. Again, it's really the same like you do it without the TOpt. You just say, okay, in which regime you would like to run the solver, what is your fluid properties, some kind of multiphysics if needed, turbulence model, rotation, in the simulation parameters, so how many cores you have available or how many nodes you have available on the Linux cluster machine, for example, runtime evaluate quantity. So you also need to be sure that all the simulation for all the variants will be converged, right? So you need to have a little bit more iteration than for a usual case. You need to adjust wider averaging to really have smooth, constant average solution at the end, for example, the efficiency. And you need to keep in mind that this must be satisfied for all the variants, right? Because if you use high twist or whatever parameter which makes the flow very wild, then it may happen that the convergence is not achieved. So you will you need to check at the end if the best parameters or if parameters of the best solution is converged or not. So you need to also keep in mind that all the simulation, let's say, is converged, which you will see directly from the report. For example, here is the optimization running, which I ran before the webinar, and anytime you can go to the TOpt browser, which is here. Okay, you can create, if I go here in the TCA menu, anytime you can generate the report and view the report, and in the report you will see the current process of the optimization. So you can check it if everything goes well, if the parameters are in the appropriate range. And of course, if I open HTML view, you open the report and you can see all the CFD reports of all the runs. So if I for example go for the run 3, I can check the convergence of residuals, of the efficiency, yeah, and for example, yeah, everything what you need. Then in the TOpt, you can show the TOpt report of the current run. Yeah, it will go up, sorry. Yeah, so this is the TOpt report with the current simulation statistics. So it's running 5 hours up to now. And this is the already revealed parametric space. Yeah, so the value of the parameters and the quantities we are follow, and basically the optimization function. So for now, the best variant is the number 6. So I can go for the run 6 to see if the convergence is nice, if everything works well. So this is what you would like to see for every report or results for every run. Great, so let's go back. So this is about the convergence. You can adjust your convergence limit. So if my optimization function is efficiency, so based on the efficiency, I would like to stop each CFD iteration. So if my tolerance is just 0.5%, which is okay for me to optimize something within this, let's say, range. So I would like to, we can set this tolerance to stop the simulation before. Yeah, so as you can see, example here, where is the efficiency graph? Yes, for example here, so here the simulation stopped because over the last 500 iteration, the efficiency changed just less about 0.5%, and this is my convergence criteria or criterion. All right. So boundary condition, again, the standard one. So we optimize it because this Axial fun runs at a constant speed and at a given flow rate conditions. So, and we would like to optimize for this. If you change it, for example, you would like to optimize for some piping system, so where is the pressure difference is the same, or you need to achieve some head or the total pressure difference, you can change it here in the boundary conditions, and of course you will probably get different design as the best design. Yeah, so everything is a complex task, and all the parameters has to be tailored to your goals. Yeah, so you really need to be careful, and yeah, optimization is basically for experts who know what is needed and what is the goal and what is possible to achieve. And standard post-processing part, just to adjust what you would like to see in the report. And the last thing, the more important one I would like to spend some time is in the TOPT itself. So the TMesh and TCFD module was the standard one, as it's very similar to what you do with a single simulation run or setup. You just need to keep in mind that if you would like to apply for a TOPT, that it means that the geometry varies, and you need to be sure that for each geometry variation the mesh is okay and the simulation converges and so on. But if not, if the simulation diverges in TOPT, you can tell what is your desired range of the output of the efficiency of the objective function, and if it is out, then then the particular optimization loop is taken out from the optimization. So let's go step by step. So in the general section, here you set the operation mode. So you can just go for the DOE if you would like to reveal the parametric space explicitly for the particular combination of parameters, or you can go for the optimization, for the optimize, where the DOE is run as the initialization, and then the optimization method or some algorithm which you choose is used for find the best local maximum or global maximum, depends on the algorithm. We have two of them, golden section search and direct. Standard algorithms you can find on the internet, the principles of it. Initialization script, so here you need to import the script which connects TOPT with the external tool. Just very quickly, usually we help the users to set it up. It looks like it's complicated, but in reality it's not. You just need to change some of the parameters here. So what is the geometry builder, the external tool which needs to be run, and basically this is a standard which looks for the script, and here you will just tell what is the templated script in which the parameter has to be changed, and here how to run the geometry builder. For the next release, we would like to simplify this and make it more easier by several clicks directly in the TOPT menu to connect the external tool with some script which includes the data of the external geometry tool, and this will be automatically connected into the topt. So it will be much more simpler in the next releases. So the initialization script is just for the connection. Convergence checking script is if you would like to apply some specific convergence check. So for the topt here, tracked quantities, optimization function here. So here is the efficiency as an optimization function. And if you would like to have a specific convergence criterion, how to stop the topt loop, you can again import it here and just tell the topt how to stop the optimization loop. Here you set just how many runs you would like to run. So for this study we used 500 runs. And now here you preset optimization parameters. So basically the optimization parameters in this case corresponds to the design parameters of the blade. So we have here chord, we have twist, thickness, and number of blades. So as number of blades, we have a list of integers from 6 to 11, which can vary. For the chord, here are the minimum and maximum values. Here are just the data type is real or integer, and what is the function of change between the minimum and maximum. So it can be linear space, log space, list. So it depends on the particular parameter, but usually we use linear space. And number of samples, this means this is for the DOE. So choose for the DOE 3 samples. So it's linearly distributed. So minimum, the value in the middle, and the maximum. For the parameter 2, there is a twist, again with the minimum and maximum range, and with 3 samples for DOE, and parameters 3, which corresponds to the thickness, is minimum and maximum, again 3 samples. And just to see here this templated script, so this is the output of the OpenVSP where you change these values. So this automatically topt changes. So these basically these names corresponds directly to what we have set in the topt here, right? So thickness, twist, etc. So this is the design parameters. So all these parameters varies. First for DOE and then to optimize to find the best combination to achieve the best efficiency. And then you can choose what quantities you would like to follow. So first one is the efficiency, which will be also used as a optimization function or objective function. Quantity 2 is the total pressure difference, and quantity 3 is the power. Why to follow more quantities than just the objective function? The reason is that for example, here you can set the accept range. So if the simulation gives us the value out of the range, then it is taken out from the optimization, and the same for all the quantities. So again, so meaningful efficiency, we know that it can be more than 90%, and values lower than 10% means usually that the design is out of the functional range of the boundary conditions, for example, or it diverges for some reason, for example. And the same holds for the total pressure difference. So we know that the total pressure difference must be positive, so it really pushes the air, and maximum, we know that it's nonsense to have more than 1000 Pascal, for example, for this particular design. And here in the optimization function, we have the efficiency. So directly we can choose one of the quantity here. Yeah, now I click on this cross button, and we are optimizing it for maximum. And we would like to run, if you set relative or absolute tolerance to 0, which means we would like to run all 500 runs for the optimization. But for example, you can tell absolute tolerance of 0.5%, which was similar to the TCFD convergence criterion, and the simulation can stop before all the runs defined here are executed. So after that, after this setup, you will just click on Run button and the simulation is running like I did a few hours ago. And then during the run, you can follow the current run which is running. You can create several windows here to follow the quantities you want, which you do pretty easily. So you can split the view. Then you can here go for TCFD for quantities. And from the display section, you can follow any quantity you want. So I don't want to have mass flow, and I would like to see what about, for example, this total pressure difference. And you can, for example, focus. So from the 0 to, I don't know, 100, let's say, okay, to see the current total pressure difference. And here in the TOP browser, you can follow the mesh of the already simulated designs. So if I make it, for example, if I go to the TOP, the result geometry, I can go for surface with edges, for example, or the wireframe. I can go here for the transparency. Okay, I would like to see just the blades. Okay, so for example, in this way. Yeah, let's go back. To this parameter, I can change the color if I want, like here. So maybe white will be more visible. Nice. And now I can choose, for example, the best design for now was the 6th design, I guess. So I can jump into the 6th design. So now the results for the 6th design is loading, and then you will see the particular shape and particular parameters for the optimization run. And of course, anytime you can go on the disk. So here is my current case running for the Axial fan optimization, and all the simulation are stored in each run. So if I would like to see the simulation run 6, I can go to the TCFD, to the stationary results, and I can again open it in ParaView and to see the particular values of the results. And this you can do anytime in new windows, in a new window, ParaView window, so you can have as many instances as you want. Now you can look what is happening inside, for example. You can look for the velocity. Now we can focus on the streamlines, for example, and yeah, you can really play as you want with the results to, for example, investigate the best design you have. So I can, for example, just the rotor blades in the hub, for example. Yeah, and for example, the pressure on it. So you can play as you want. So as depicted, I think in the study, you can then go for the analysis, for example, of the best design and really make the views you want to see and you want to present, for example, to somebody. All right, so I think I'm almost at the end. So probably, oh, and yes, we can go through the final report. So if the simulation is finished, you will see the TOP report of this size. So just to sum up, at the beginning you will have simulation statistics. So this optimization takes like 5 days, so 120 hours on 24 core machine. Yeah, number of runs was 400 for the final simulation, and here is the parametric space for all the 400 runs. And maybe there is also example, for example, here where the efficiency was out of the range. Yeah, so this 75th run was taken out from the optimization because one of the parameter, which is I think the efficiency, yeah, was less than 10%. So it was taken out because maybe there was something wrong, or maybe the design was out of functional range. Yeah, because for example, this icon shows you or intends you if it's okay from the simulation point of view, like residuals are low enough, the flow rates are the same at the inlet and at the outlet, and so on. Yeah, so this means that from the simulation point of view it was okay, but one of the parameter was out of the range, so therefore it was taken out from the optimization. And here we can see other points. So when I go a little bit lower, more low, yeah, at the bottom, so we can find the graph for all runs and the values of total pressure difference, efficiency, power, and optimization function. And also there is highlighting point which gives us the best efficiency point, which is then presented in a separate table. So the efficiency of the best point was 47% with the given parameters with the 7 blades. And yeah, you can then go for the particle simulation to be analyzed more deep. Then there are several functions which reveals the parametric space. So here we have the dependence of the optimization function on the number of blades. So the best efficiency is achieved for the 7 blades. The short length is almost for the highest we said. The thickness again is the best efficiency is reached for the almost the lowest, which somehow makes sense, right? But because the thinnest blades usually have the lowest drag, for example, if you can speak very in the simple way. And then the same is done for the 3D graph. So there is dependence on the two parameters with respect to the optimization function. So let's say what is the dependence then between chord length and the thickness. So and how optimization function is reached, and you will also see how the optimization where the optimization parameter looks for the best optimization function or for the best efficiency. And again, the same for the 2D graphs. So efficiency versus thickness, and you will find all the combination of all the design parameters with all the tracked quantities. All right, so everything is concluded in the report, right? And you can go by own, you can download the case, you can contact us and do the analysis by your own. All right, so maybe it's time to go back to Luboš, if he is still there.
And he is. He is. Yes, I am. Yes, Radek, thank you very much. It was really great. I liked it, and it's I still like it, and it's great. So thank you for your part. And now I would like to ask the audience to ask the questions. We will do our best to pick the most representative questions, and we will happily answer them. I have a couple of points I was following very carefully, and I made a couple of notes here. So I'd like to point a little bit. So first of all, maybe, I don't know, but maybe for the newcomers, for the new people in the field, the whole workflow may look a little bit complicated and very complex, but it only looks complicated, but it's not. it's relatively straightforward, but it needs some experience, it needs some practice, which definitely eventually comes with time spent on any project. So you can remember that no one is a champion riding a bike for the first time, but eventually over the time things go much easier. So it's not that complicated as it looks like. That's my first point. The second point is it's the TCAE is not just a software, right? It's not just a piece of code. It's a partnership. It's a being part of our big family with us and our users, and it's definitely not just a software. It's a knowledge. It's a knowledge base. It's a technical support. You're never alone, and you can always get back to us, and we will gladly help. So you definitely are receiving not just a software, and also a know-how, which is valuable, and we always we never leave our clients behind. That's the second point. The third point is we have chosen a couple of parameters for this optimization, right? As you can see, maybe I hope you can still see this little animation. There's this number of blades and this short thickness twist. Those are 4 parameters we have chosen. So of course, you can pick any parameters and any number of parameters. It's always up to the user. So we have chosen just these because from our previous experience, we know that these parameters matter. But of course, for another engineering office that you might be interested in another set of parameters, that's absolutely okay. The workflow is the same all the time, and the principles are the same. So we have just chosen these 4 parameters, and it doesn't mean anything. The same, the followed quantities. We know that for fans, pressure is important. The power, of course, the power consumption is important. And finally, we have chosen as the optimization function, the objective function, we have chosen the efficiency. Again, it's absolutely customizable. So you can choose any quantity or any formula. You can say, okay, I'm interested in and the objective function which is 40% of efficiency and 60% or 40-20 and 40% of power pressure or whatever it can be. It can be the fan damage. It can be really anything. So it can be a very complex formula, by the way. So it's not just the efficiency. Efficiency seems reasonable for us because it somehow includes all the important quantities as the pressure and power and the torque and these quantities. So it's kind of important for us, and also we're living the world we want to make better and better, and the efficiency somehow concerns all these facts, I would say. So it's this, and okay, so it's these are my points. I have a couple of other points, but let's make this quick. So Radek, can you see some questions you would like to answer?
Yeah, well, I see 2 of them, but maybe both it's better for you to answer. There is what would be the approximate cost of this optimization on AWS? So
yeah, good
so
question.
It depends on the pricing, right? So we have used 120 hours times 24 cores, right? Time cost for the one hour per core, right?
Our clients can use who have the license. They can use freely the TCAE on the cloud. So it's just there. It's just the price for the iron. We call it iron. It's just the core hours. What's paid, and it's the current policy. So it's the price of core hours on the cloud, and Yeah, what else? Can I? Daniel is asking, can I use TCAE for generation of the geometry and OpenFOAM to run the simulation? Well, that's what it is in TCAE. So it if I get it right, it wouldn't make any sense to use just part of this and then OpenFOAM. Of course, you can create your own workflow, right? So you can use OpenVSP and script everything. It's not that difficult as it looks like. Yes, you can have a like free uh, open source software on your own, but it's not that easy. Remember, we have spent 40 plus many years on development of this, so it's very difficult, and it's fair enough. With pure open source, the price you pay is your time and effort. If you want to get it quickly, a professional solution like TCAE helps you to get where you want very quickly, but you pay for it. It's a classical trade-off between time and effort versus costs. So that's as simple. And what else? How many objectives are tackled? Adel is asking at once. You can create your own objective function. So it's up to you. So you can. Well, maybe we have a misunderstanding here because the next question is why efficiency is only about. Yes, yeah, the efficiency of this fun is not very high, but can it's in the range. Certainly, it's in the range. But yeah, it can be. I think we know it can be more, but we have this rule of let's say large blades, but we know it can be better. Yeah, it's a good point. Yeah, but
Maybe
this
I have
study
just a
is
point that
correct.
this is the efficient. May I interrupt you? Because it's
Yeah,
efficient for the whole domain, including the chambers, which was part of the original design. So it's
yeah,
not the efficiency of the just inlet before the fan and at the outlet, just in this shroud section, right, or casing, but it's for the whole domain, including the chambers. So it also depends, yeah, on the
yeah,
losses which are gained in
yeah,
the chambers.
yeah.
So I think
Yeah.
the efficiency will be much higher
Could be the reason. Could
for
be the
just
reason.
for the rotor. Yeah.
Yeah, thank you, Radek. Yeah, could be the reason. Yeah, it's not very high. Yeah. Okay, and Bistrik, hello Bistrik. Yeah, he's asking, can OpenVSP replace function of Geometry Builder? Well, it's actually what's it about. Yes, it has replaced. It is the OpenVSP is the Geometry Builder in this case. So it receives a set of parameters and it creates the geometry, and then the rest is standard TCAE, where TMesh creates the mesh, TCFD runs the simulation, and the opt decides what will be the next set of parameters, and the other, yeah, and around the workflow, the loop continues again. The OpenVSP creates the geometry, so it works as a geometry builder. So I hope you understand each other. And yeah, and Radek, can you see anything else? Frederick is asking question.
Okay, maybe, yeah, the Frederick's question about the accuracy, if I understand it correctly, so for the second loop, we would like to, for example, create the mesh much finer, yeah, with all the aspects for the more accuracy, and then you would like to run, just conclude if the best design is still best design. So the workflow will look very the same. You will create a copy of it, so you will save the project as a new. You will preset new meshing, and base, for example, you will set the TOP as a DOE and pick up, I don't know, 10 combination from the parametric space you did. It's best design, some design close to it, some design far from it, and run it again if you still get the best design for the best design of the previous optimization. So if this is if I understand you correctly, The workflow will be very the same, like you just pick up the point you want from the parametric space, and or you can shrink the parametric space just along the best efficiency from the previous design and run it on finer mesh. So but in general the workflow remains the same, you just change some parameters.
Sure. And also later in when having the database, right, it will be even better, but that's another story and story of the future. Okay, we have typically we have questions about if there will be a recording. So yes, there will be a recording of this webinar on our YouTube channel, and we will there's an automated email which sends you to everyone the recording. So yes, the recording will be of the webinar will be available, and all the details are available on our website, and also send us an email. We will gladly answer all your questions. So it's definitely very transparent, repeatable, and open workflow. And Radek, I think it's time to move on. So I will close this Q&A. Yeah, actually we haven't. Yeah, this slide opens the Q&A. So now I'm closing the Q&A, and if I should say one last thing, if there is a lesson, just one lesson to take, one takeaway from this, it's impossible to recognize what's better or what's worse by a human eye. We did a little homework, and we have picked of course the best design, and we have picked 3 other very similar, for human eye, very similar candidates or designs during the round. So it's the most efficient, the best design. The set of parameters was run number 370, and we have picked 3 similar runs, which are by human eye. They are very similar. They look very, very similar. They're not the same. They're different. We checked many times. They're really different in little angles and thicknesses and things. And but what you can see, the human eye sees approximately the four same fans, right? The four same impellers, 4 same blades. But the efficiency of the first one is 36%. The efficiency of the second one is 40. The efficiency of the third is 43%, and the last one is the most efficient, 47. And the human eye can't recognize. You can only see the little details, right? This is definitely smaller than this gap, etc., etc. But you can't decide what's more efficient. But the simulation can, and it can iterate, and it can give you the best possible result. That's a big difference, and that's the why we do this, and that's the benefit of such an optimization workflow. Okay, Radek, can we switch the camera on to show the audience? It's us, it's live people, not just the artificial intelligence, right? Not something. So, yeah, I'm joking. So I think it's time to conclude. Yep, the last slide we had, it's for 5 years the same. We should change it. That comes the first on my mind. Here, it's a couple of those who already share our visions with us, and we hope others are on the way. Everyone is welcome in our family. We believe there's a lot of at stake. The field is changing very quickly. We are following all the latest trends and developing. We put all the profit into the new developments, and we are moving very quickly. So we believe you will be with us on this way, on this journey. And yeah, I think this would be it for today. Radek, what do you think?
Yeah, I think the webinar is long enough, so just let me thank you, and see you next time somewhere, or contact us, and we'll gladly discuss everything what you need to discuss. So thank you, have a nice day, and see you next time.
Yes, we will. So thank you for coming. We will do our best to support you. It's our job, and also a pleasure, and we will leave you with that. And bye for now. Bye. Thank you for coming. So, and I need to